Hello, my name is Nicholas Wiley, and today we're going to be calculating the fanning friction factor, or the friction factor, using Python coding, and then we're going to be applying this to two different situations, which we will also be using Python coding to solve. So the first thing we're going to do is we're going to describe the first situation that we are given. Now, the first situation we are given is that we are going to have a flow rate that we are going to want to achieve based off of our head drop. So what we know about our flow rate is that it's going to be equal to our velocity times our cross-sectional area. I'll get to why that's important in a bit. So another thing we know about this system is that we have a flow rate that we are trying to achieve, and we have a pipe with a constant diameter. It is non-changing. Because the diameter is not changing, that means that the velocity is going to be constant. So what we can do is we can get rid of this term, because this is going to be 0, as the velocities are going to be the same. Now, another thing you may have noticed is that this looks a little bit different than our last video when we were trying to figure out an expression for the fanning friction factor. What we've done is we've divided everything by g in our entire expression. Now, why did we do this? Because our units for both this piece and this piece right here are going to be dependent upon, are going to be in units of meters. And that gives us a little bit of freedom of design of our whole system, our pipes, and all of that. So if we wanted to, we can make it based off of just gravity dependent, based off of altitude changes, or we can make it a situation of pressure differences in which we use something like a pump to achieve that. Now that we got all that out of the way, we have the left side sort of figured out. This is going to be our head drop since it's all in meters. What we can do is we can talk about, again, what we talked about in the last video, is that frictional heating term over there. Now what we did is we figured out this is going to be -4 delta x, which is going to be the length of our pipe, multiplied by F, our fanning friction factor. We'll divide that by our diameter multiplied by G, again, because we are in head form. We also need our V squared over 2 term. Now, when looking at this expression, what we need is only a couple of pieces left. So we know our diameter, we know our gravitational constant, so those are both checks. We also know our length of our pipe, that's going to be given to us. So all we're going to be left with is this velocity piece and this fanning friction factor piece. So the reason I wrote this before is that we need to find an expression for this velocity that we can break it down a little bit more with terms that we know. So what do we know? We know the cross-sectional area of our pipe. Real quick though, let's reorganize this because again, we want an expression for our velocity. Velocity is going to be equal to our flow rate over our cross-sectional area. What do we know about our cross-sectional area? It's going to be equal to pi d squared over 4, pi r squared, but multiply it by 2, square that, you get 4 on the bottom. So what this is going to become is it's going to become, so we have pi d squared over 4 on the bottom, so we have a denominator and the denominator. We pull this 4 up here, and we divide by pi d squared. So now all we have left is this F right here, this fanning friction factor piece, and that's what we're going to be coding. Now, we're going to base this expression off of many different people's equations. Many different people have come up with different ways that the Reynolds number and the roughness of our pipe is going to change that friction factor. So what we're going to do is we're going to check out some Moody diagrams. We're going to pick which one that we want to use, which will be the Churchills. And then from there, all we'll have to do is code that in, figure out our fanning friction factor, and then we'll be able to determine what our head drop is for this left side that will help us achieve this given flow rate. So again, this fanning friction factor, our friction factor, is going to be based off of the Reynolds number and the pipe roughness, and we're going to be looking through Wikipedia, Moody diagrams, and select our choice, and then hop right into the program, the Python coding, See you in the next part. Alright, so hello everyone, we're back, and what we're going to be doing is we're going to be discussing the Moody diagram and the Churchill equation and how that's going to help us get into the Python coding that we have. So if we go over here, what we're going to see is that we have a Moody diagram, which is going to give us a sort of relationship between the relative pipe roughness and the Reynolds number. Now, as we've discussed, there are many different people who came up with different equations or relationships, if you'd rather, for how the relative pipe roughness and the Reynolds number affect the friction factor. As we can see from this diagram, this is going to be our laminar flow. Our friction factor is going to be 64 over the Reynolds number. Now, in the last video, one of the last videos that we had, what we did was we derived an expression for laminar flow for the fanning friction factor, which is 16 over the Reynolds number, so we'll keep that factor of 4 in mind. and also the fact that all of these equations are going to be based off of this value right here, 64 over the Reynolds number. So if we head over here, we're going to be talking about this Churchill equation right here. Now, looking at this right here, it actually looks like a lot, but it's actually pretty convenient. The only thing that's going to be a little difficult is syntax, but luckily I have something for that that'll help us out. So looking at this, what we see is that this is not going to be a it's not going to be a nonlinear relationship, because that would make things a lot more difficult. Rather, what we have is we simply just have some inputs that we need to put into our program, and we'll be through with it. So again, this is what we're going to be using for our friction factor calculations. And what we're going to have to do, as I've said, is that this is a factor of 4 increased, the friction factor that is going to be used in these equations. So all we're going to have to do is multiply this value by 2, and we are going to be smooth sailing from there. Now we'll hop into some Python coding. So what I've had is I've pulled this up, and we have a couple of imports that we already have. So first up, we have numpy as np. What we're going to be doing is we need numerical Python to do a lot of our things, such as square root and using the value pi, which we're going to be using. In square root, of course. And then this is going to be for a later part, but pretty much what this is going to do is this is going to help us solve a nonlinear equation in the second situation. Right now we're going to be talking about the first situation, which is the friction factor, as I've stated. Now, a couple of things that are also going to help us in the future, but I thought I'd get them out of the way for us, is that we have these 3 constants right here. First up, we have rho, which is going to be the density of water. It's going to be 1e to the 3. And that is going to be, let me comment units, I guess, is going to be in kilograms per meter cubed. And then we also have the viscosity of water, which is going to be 1e to the negative 3. That's going to be units of Pascal seconds. So Pascal times, oh, that's a plus, my bad. And then we have g, which is going to be 9.81. That is going to be in meters per second squared. All right, now that we have that out of the way, again, this won't be relevant to us now, but it will be relevant in the second situation. What we can do is we can start and go ahead and plug and chug through our Churchill equation. So what we're going to do is we're going to define a Churchill equation. And for our function, what we're going to need is we're going to need to supply the Reynolds number, and we're also going to need to supply our surface roughness. Now, the things that we need to input for this, a sip of water. We are going to need to use these equations right here. So we need to define theta 1, theta 2, and then we need to use this equation right here, multiplied by 2, as our return for the function, because that is going to give us our friction factor at a certain Reynolds number and surface roughness. So what I've actually gone ahead and done is I've created this right here to help us with syntax and also to help us get through things a lot smoother. So what I'm going to do is don't get mad at me, I'm going to copy and paste this. Made sure to run this through first, so hopefully it works, unless there is a small syntax error. So we have our theta 1, as I said, which we need to define. We have our theta 2 right here. Again, this is just from the wiki article. And then what we're going to need to do is we're going to have to use those 2 terms together. What we're going to have to return is this value right here. It's going to be, again, like I said, 2 times whatever this value is. Am I missing a parentheses there? 1, 2. We may be missing a parentheses there, actually, now that I'm looking at it. So we'll see if we get a syntax. Oh, no syntax error, so I think we're good. So now that we have this put together, what this is going to do is it's going to use this Churchill equation. It's going to return back the friction factor. So now what we can do is we can supply it with a couple values. Now, looking at this chart, we can supply any 2 values that'll give us a friction factor. And we do have to remember that it is going to be 4 divided by 4 of whatever this term may be. So let's go for about 0.04 so that we end up with about 0.01, which is around the value of the fanning friction factor that we will use for a F-guess later, which you will see as we get to it. But if we move along here, we can find that, actually we'll go a little bit below. We're going to try and find something that's pretty close. Okay, so this line right here is going to be 0.01. That's going to be our relative pipe roughness, okay? And then we have 10 to the 6th for our Reynolds number, as you can see on the bottom. So if you see my cursor right here, and this should be around 0. This looks about 0.0, maybe 38 somewhere in there. So if we divide that by 4, we should get about 0.95, 0.0095 for our friction factor. So let's go ahead and do that, just making sure I have it all lined up. So what we're going to have 10, 1e to the 6th, comma, and then we'll use 0.01. That is going to give us just about 0.0095, as I've just said, as we can see from here, because it is divided by a factor of 4. Now what we're going to do is we're going to go ahead and in for our head drop. Let's go ahead and start that. What we're going to supply this is going to be our flow rate that we want to achieve. We're going to use our length and our diameter. And a couple other things that we need to include under this function is we need to first supply the velocity, which as we had before was 4q divided by pi times our diameter squared. Okay. Next up, we need to supply the Reynolds number, which if you're an engineer and you don't have this memorized, then bad on you, that's not good, which is going to be rho multiplied by our diameter multiplied by our velocity of our fluid, and we're going to divide that by the viscosity of our liquid, which we are going to use water, as I've defined up above. And now we need to supply our friction factor, which is going to be our Churchill equation, same inputs, which we are going to have the Reynolds number and the surface roughness. And we're also going to need to include that in here, as we are using that, and we need to input it. And what we need to return is we need to return the right side of our equation, which if you remember was the frictional heating term divided by G. So what we had was we had the 4FLV squared over D times G, V squared over 2, and then we have 4 in the numerator, so 4 over 2 is 2. So we're going to have this 2 multiplied by our length, multiplied by our friction factor, multiplied by V squared. And what we do is we simply just divide this by our diameter times G, our gravitational constant. Shift enter on that. Everything has been shift entered. It is all active. Now what we can do is we can make sure that we can figure out what the head drop needs to be for our flow rate, which we will say is 0.1 meters per second. Our length we can say is 10 meters. Our diameter can be 0.1 meters. And we can have our surface roughness to be 5e to the negative 3. And what we get is that we need to have a head drop of 25.18 to achieve a flow rate of 0.1 with a 10-meter pipe length, as I just explained. So what does that mean for us? What this means is that we have our system. If you remember from the first part, I said having it in head drop form allows us to do to manipulate our system, our pipe a little bit. So what we can do is we can say that this head drop can be caused by either the altitude or gravity or by the pump. And because we have this, we're saying that this 25.18 meter head drop can be a mixture of the two. It can be just one, it can be just the other, and that's really good for us. So now that we finish this, what we're going to do is we're going to go to a second situation, which I will explain in a second. The second situation that we're going to have is we're going to have pretty much the opposite of what we had before. We're going to have a known head drop, and we need to figure out what flow rate will get us to that certain head drop. Now, we encounter an issue with that. When talking about flow rate, velocity comes up in a couple of different places in our Bernoulli's equation in our whole system that we had set up in the beginning of this video. Where does it appear, you may ask? First, it appears in the Reynolds number. Secondly, it appears in the flow rate itself, and then it also appears in the fanning friction factor itself. So we have 3 different places where this is going to show up, meaning that we're going to have a set of nonlinear equations, which is why, as I said in the beginning, I'd explain why we need it. We will bring in SciPy optimize the root function. Now, I've had this problem. I know it's not going to work, but pretty much what this is going to do is this is going to help us minimize a difference between 2 functions that you will see in a second, what we're going to need to do is we're going to solve linear problems. We're going to supply it with a guess, and then it's pretty much going to drive our whole equation to 0 that we're going to put in right now. So let's go ahead and just get into it. It makes more sense as we go. So pretty much this, like I said, this is going to be the opposite. We have flow rate, and then instead of Q, what we're going to have is we're going to have our head drop, which we are going to call beta. We're going to have our length, our diameter, and our surface roughness. And instead of going right into what we're going to need to supply this, what we'll actually do is we're going to define the function that we are going to be driving to 0. Sorry, put that right there. So we're going to define an equation, supply it with x. What we're going to do is we're going to make a set of flow rates, Q, and what we're going to do is we're going to say that this is going to be, we're going to create a vector, as you can see right here. The reason we're doing this is because we're pretty much just going to iterate until we've minimized the difference, which you're about to see, until it hits 0, and then we can figure out what our flow rate is going to be to achieve the head drop that we have been given. So where are we going to need to return? As I've just said, we're going to want to minimize an objective function, and for that, what we're going to return is we're going to return our beta minus the head drop that we have before, and luckily we have this equation. So what we'll do is we'll go ahead and we'll supply it with the same things that we had before. And I'll just leave that there for now. So the thing about SciPy optimized root, and again, I really wish I could pull this up, but I can't. So what you need to do for the SciPy optimize the root aspect of it is you need to supply an initial guess. Now you may be asking, how are we going to provide an initial guess when we have so many varying lengths, diameters, the surface roughness? Well, what we can do with that is we can actually create a sort of function that we can use to create that guess. So pretty much what we're going to do, you'll see in the next part of this video, is we're going to derive an expression that we can use for our initial guess. Now we need to create an initial guess for the flow rate of our system for the root solver that we're going to be doing. And the best way to do this is going to be using the flow drop in relation to our frictional heating factor. So what we're going to go ahead and do is we're going to use beta, which is going to be our head drop. Now an interesting thing about the beta is that, or the head drop, is that it's going to be equal to the negative left-hand side of Bernoulli's equation. And if we remember, correctly, we can see that this would be if this were the left-hand side was not the head drop and it was in the form of Bernoulli's equation. Since this is the opposite, that is going to make this positive. Now, what do we know about this this frictional heating term? We know that this can be broken up into beta is going to be equal to, since this is positive, it's going to be 4 delta x multiplied by our fanning friction factor. And what's also going to be very helpful for us is that our fanning frictional factor is going to be a very small range of values, so we can make a pretty accurate guess, as again it is a very small range of numbers. What we're going to do is we're going to multiply this by v squared over 2, and multiply this by g, as again we are in the head form. Now, what can we do with this expression? What we need to do is we need to reorganize for our velocity, and then we can create that into a flow rate expression that we're going to use for our initial guess. And what we're going to have to do is just multiply that by our cross-sectional area. So let's go ahead and do so. So what we're going to have to do is we're going to multiply this by the denominator. So we're going to have 2 beta times d diameter times our gravitational constant divided by 4. So we can put the 2 down here actually. 2 delta x times f and our fanning friction factor. And again, delta x is just going to be the length of our pipe. Then since v is squared, what we'll do is we'll take the square root of that. So now this is going to be an expression for v. So all we have to do to get to our q, our flow rate term, is simply just multiply this by our cross-sectional area, which is going to be pi d squared over 4. And that is going to be the expression for q, our q guess that we need to complete our Python coding. Before I go ahead and finish this up, I thought that I'd make a couple little corrections to my code from the last part. first and foremost right here, I forgot to create this as an array or a vector. Now what's the issue with that? As I've said, we're going to be driving this expression towards 0. So what we need to iterate over time until our solution is reached. So we need to have this be a vector or an array quantity. So in addition, what we can do is we can talk about our fguess value. Now when we're looking at this Moody diagram, what we see is that we have all these values which go all the way up to 0.1. Now I'm going to tell you that our guess is going to be 0.01. Why is that? Because again, we have this laminar flow value compared to our fanning friction factor. This is going to be divided by 4. So when you divide all these factors, these numbers by 4, what you're going to end up with is pretty much that small range is going to lead us to about 0.01. So that's going to be our fguess, not that. Okay. Now what we're going to do is I have conveniently grabbed this right here for us, again for the syntax reasons. So we have that qguess, and we have this right here, which hopefully is correct with syntax. And then what we can finally do to end off the video, almost end off the video, is we're going to return the root of our equation and the vector of our qguess, making sure my syntax is correct. We're going to use that x value. Define equation. Alright, so hello everyone, we're back. I had a little bit of struggling when going through here with a lot of syntax issues, as you saw when I just cut. Pretty much what I had wrong was I had my returns in the wrong spot. I also missed this parentheses right here, which took me way too long to figure out, I may add. It took me reading it over. I was looking through a bunch of different syntax problems that I knew that I was having. So I believe this return was in the wrong spot, and then this syntax was off, which just kept telling me that these two expressions were off. So after a little bit of troubleshooting, I believe we finally got it. I think that's really all I changed. It was just a couple minor fixes. I apologize for the cut. Excuse me. Now all that's left to do is insert these up here, which for our beta we'll use this head drop, and see if our flow rate is going to be 0.1, 10, 0.1, and 5e to the minus 3. Shift enter, and praying we get 0.1, fingers crossed, and we got, yep, 0.1. So that ends the video, starting off with figuring out the friction factor, Python coding that into here so that we can figure out the head drop necessary to get us towards that 0.1 flow rate, and then reversing it and given a certain head drop, figuring out what our flow rate needs to be to get there. Use scipy optimize.root to get the second part, and then the first part, just simple function with a few different things that we had to input, and that'll end the video. I apologize for the troubleshooting, but hopefully you still enjoyed, and I'll see you next time.